Alright, welcome back. So now we are going to solve a few problems and I'm also going to introduce you to some of the formulas. So in our first formula it says it's an air core inductor and it has length 1 meter and number of turns 100 meters and area of cross section 0.1 meter square. So what it means is I'm going to draw this out for you. So let's say there is a piece of cardboard or something like that and it is 1 meter long, and usually it's not going to be a piece of cardboard, but let's just, for the sake of the problem, assume it is. And we have our conductor wound here across this. Remember, that's just an inductor, and it is wound 100 times, so that is our number of turns n. And this is looking at the top view, and so if you look at it from the front, it's going to be a circular core. You're just going to see a big circle like this, and the area of this circle is 0.1 meters square. So we are being asked to find what is the inductance. So if you guys remember, inductance is a term that relates the induced voltage to the rate of change of current. So the faster our current changes, the more our voltage is going to be, but we need a term that relates to it. So that is our inductance, and we are being asked to find what is the inductance. So there is a very simple formula, and it's L inductance. The symbol for inductance is L, is mu naught times n square area by length. N is our number of turns, A is the area of cross section of the core, and L is how long is our inductor. So I gotta explain mu naught. So mu naught is called permeability of free space. And this has a value of 4 pi times 10 power minus 7 Henry per meter. So remember, the operation of an inductor works mainly by storing electrical energy in the form of a magnetic field. So when you have a magnetic field, you have magnetic field lines. And not all materials allow magnetic field lines to pass through them at the same capability. So you have your ferromagnetic materials like iron, which allow a lot of field lines to pass through them. And you have basically inductors and all other materials which allow magnetic field lines to pass through them at a relatively low extent. So this is a measure of how many field lines a material allows to pass through it. Alright, so in our problem, it's air core. So basically, this core is hollow. There's nothing but air. So that is a measure. This is a measure of how many magnetic field lines regular air or free space allows to pass through it. Alright, so to find the inductance, now it's pretty much straightforward. Our mu naught value is 4 pi times 10 power minus 7 into a number of turns is 100, and I'm going to square that, times area of cross section is 0.1, and the whole thing divided by 1. That is my length. And so solving this, I'm going to get 1.25 into 10 power minus 3. I can just write the 10 power minus 3 as a milli and Henry. Alright, so this is going to be our final answer. So you do not have to worry about finding really difficult problems to solve in your FE exam. It's going to be pretty straightforward. This, you can find it in your reference book. But if you're not taking the FE exam and just watching this video, otherwise, it's fine. It's a pretty straightforward formula. Don't even worry about memorizing these. Just know it relates to the number of... So if you want to look at it a different way, the inductance is depending on certain terms, right? So if you want to increase your inductance, you can either increase your number of turns, or you can increase your area, the area of the core, area of cross section, or you can use a different material which has a different value of mu. So those are some of the different ways you can increase or decrease your inductance. Alright, so let's go to the next problem. So our next problem says we have an inductor of inductance 5 millihenry. It's got 100 turns and the current goes at 0, or the point of reference is 0, so we have 0 current, and at the end of 2 milliseconds it is 100 milliamperes. So we have a change in current. Alright, so let me write it down. So our DI in 2 seconds, 2 milliseconds is 100 milliamperes. So it goes from 0 to 100 milliamperes. And we need to find what is the induced voltage. So if you looked at the video that so the inductor is going to have, when the current flowing through it changes, it's going to have an induced voltage. And we're being asked to find what is that induced voltage. And if you look at this formula, this formula relates voltage and induced voltage to the change of current. And that is what we're going to use now. So we got our change of current as 100 milliamperes, and we got our inductance, we got our number of turns, and we got to find the induced voltage. So the induced voltage here is going to be inductance times di by dt. But right, no buts, sorry about that. So it's going to be direct substitution. We got 5 millihenry, that is our inductance, and our di by dt is 100 milliamperes, and our dt is 2 milliseconds. So it goes from 0 to 100 milliamperes in 2 seconds. So if 1 millisecond, 2 milliseconds time. And let me see, 50, 100. So this is my current. So my current goes to so that is sort of like the rate of change of current. I am not sure if it's going to be linear or so. Let me erase this. Yeah, I don't want to risk giving wrong information, but let's carry on with the problem. So if you solve this, you would get your voltage across the inductor as 0.25 volts, right? So 10 power minus 3, 10 power minus 3 cancels, and we got an $50. So we got 250 times 10 power minus 3, so that's 0.25 volts. So this is the induced voltage. Alright? Pretty straightforward. So you cannot expect very difficult problems in your FE exam, so it's going to be pretty straightforward. All you got to know is your induced voltage relates to the change of current with respect to time by this formula. So if you know this formula, you can pretty much substitute it. But yeah, then again, you got to know how to find what is di by dt. So this di by dt is simply the small amount of change in current with respect to the small amount of change in time. So this is dt is 2 milliseconds, di is 0 to 100, that's 100 milliamperes. Alright, so let's go to our next problem. Okay, so now I have my inductance value given as 100 millihenry. That's for my inductor, and the current relates with respect to time as t square. So my current at 0 is going to be 0 square, that's just 0, and my current at 1 second is going to be 1 square, it's 1. I am not sure if this is amperes or milliamperes, but just going to consider it as 1 unit. my current at 2 is going to be 2 square, that's 4. So it's an exponential growth. So if you have an inductor, let's say 5, 10, and we are being asked to find the energy for current flowing for 10 seconds. So because in the inductor is basically a component that stores energy, so it starts at 0, and at 1, 2.5, it is an exponential growth. So in response to my previous question that I asked myself while solving this problem, the inductive current would rise like this. Alright, so we're being asked to find the energy. So this is the current, and this is time. So our current and time are going to increase like this, and we're being asked to find the energy if the current is flowing for 10 seconds. Alright, so I'm going to skip through all of this and just find my current at 10 seconds. So my current at 10 seconds would be 10 squared, which is 100 units. Let me check that real quick. Alright, so I have missed out some information. This current is going to be in milliamperes. So this is going to be 100 milliamperes. Alright, so now I have my current value. So I have my inductance. So the expression for finding energy is given by energy in an inductor is half times Li squared. So L is your inductance, I is your current, and so we already know what is the current. It's 100 milliamperes. We know what is inductance, and now we also know how the current rises. Alright, so it's simple substitution. So my energy in an inductor, E is going to be half times Li square, inductance times current square. So my inductance is 100 millihenry. So it's going to be half times 100 into 10 power minus 3. And my current is going to be 100 milliamperes. Right. Square. Alright, so let's solve this. So it's going to be half is 0.5 times 100 into 10 power minus 3 is 10 power minus 1, and this is going to be 100 into 10 power minus 3 again. It's 10 power minus 1 times 2, so that's going to be 10 power minus 2. So that's 0.5 into 10 power minus 3 or millijoules. 10 power minus 3 is milli, so I'm just going to write it as milli. So this is my energy stored in an inductor. So let me go back to this slide right here. So we have an inductor. It opposes change in current, and it does so by converting the electric current flowing through it into magnetic field lines. So when the current flows in a circular pattern, it's going to create magnetic field lines and also an induced voltage. And because of this, the inductor is going to store some energy, and that energy is given by this formula. E equals half times Li squared. So I know what is my inductance, I know what is my current at 10 seconds. Alright, so my current at time t, so that's 10 seconds, and I know that's 100 given by the expression right here, t squared. Alright, let's solve the next one. And this is our last example. So we are going to solve the equivalent inductance of a network of inductors. So let's say you have a bunch of network of inductors and you want to find what is the equivalent inductance. And so this works exactly the same way as resistors work. So if you have resistors in series, you would just add them. So the same way, if you have inductors in series, you just add them. And if they're in parallel or if they're in branches, you use the branch formula. So let's go ahead and solve this. All right, I'm gonna erase this. So I am gonna solve, I'm gonna rewrite this branch. So I got 1 millihenry, or what, just 1 henry, sorry about that. And I got these two branches, so I got inductors in series, so I can add them, and this would be 2 plus 2, that's 4. And it would be again 2 plus 2, that's 4 henry right here again. And it's gonna have 1 henry here. So I don't know if you guys remember, but if you have equal resistances or equal inductors in different branches, so the equivalent inductance for that is going to be 1 by L equals 1 by 4 plus 1 by 4. That's going to be half. So my L equivalent is going to be 2 Henry. Alright. So another shortcut way of remembering this is if you have 4 and 4, it's just going to be half of it. So now I can write my circuit as having an inductance 1 Henry. Here another inductor of 2 Henry. And my final inductor of 1 Henry. Now all three of them are in series, so I'm gonna not call this L equivalent because I'm using that term here, so it's going to be 1 plus 2 plus 1, it's going to be 4 Henry. So if you look at this circuit, it does have a real world engineering application, because if you remember, an inductor is something that's just like a conductor wound across a core. And this you will find in transformers. Transformers have inductance because transformers have two coils, primary and secondary. And because they're just wound, so they have inductors. They are basically inductors and they have inductance. They have primary inductance, they have secondary inductance. And you will also find this in motors. So in motors you have stator windings and rotor windings. Because of that, motors will have inductance. So if you look at an electrical grid having transformers and motors, so you have your supply and you have, let's say you have a motor, that motor is going to have some inductance. So if you want to do circuit analysis, you can replace that with an inductor, which in later videos you will see that is how motors are represented. Alright guys, so that is it. I hope you guys are confident enough to solve some problems on inductors in the FE exam now. So let's run through the problem once again. Alright, let me go to my first problem. The first problem, we made use of this formula, which relates to it basically relates the dimensions with the amount of inductance. So if you have, when you are developing or designing an inductor to be constructed and you have a certain value in mind, you need to keep the number of turns, the material of the core, the area of cross section, and the length of the inductor. So those are some of the terms you need to keep in mind if you want a particular value of inductance. So here we already had the dimensions and we needed to find the inductance. So that was 1.25 millihenry right here. Okay? So the next problem that we solved was inductors have induced voltage across them and if my current goes from 0 to 100 milliamperes, what is the induced voltage? And so I had my inductance value already known as 5 millihenry, so I just plugged it into my value that says the induced voltage is inductance times rate of change of current. And my next problem, we were asked to find the energy because inductors also contain energy. So this energy is E half times inductance times the current square. So my current at the end of 10 seconds was 100 milliamperes, and it was an exponential growth. And because of that, we were able to just plug in the values and find it was 0.5 millijoules. And my last problem was a network problem. So I had a bunch of inductors in my network, and solving some of the inductors step by step, following the same rules that you would follow for solving resistor network of resistors, we found the equivalent inductance to be 4 Henry. Alright, so that is it. Good luck to you guys if you're taking the fundamentals of engineering exam. If not, I hope you got something out of this video on inductors. Thank you so much.